Hello, good afternoon, or good evening, or good heat death of the universe, depending on what time it is where you're watching. I'm Phil Lamar, and welcome to NASA's Ask the Astronomers Live, the show where you get the chance to ask real, actual astronomers questions about the universe live. All right, today we're going to be delving into NASA's Astrophoto challenges. Now, for those who don't know, these are NASA provided challenges that gave viewers like you, and in fact, I believe we have some of the Astrophoto Challenge winners here in the chat. Priyanko Devchudori and maybe a couple others. Oh, yes, there we go. Thank you for being here. And most importantly, thank you for taking the opportunity to use real astronomical data and astronomical tools to create images, beautiful images, of the massive black hole harboring galaxy called M87. That's what the Astrophoto Challenge was. Now, for those of you who are joining us live on Facebook or on YouTube, please use your real names. And also, make sure you say hello in the chat, like Priyanka did. And definitely, as we go on, send us the questions that come up. We want you to leave here smarter than you came in. And be sure to visit the website, universeunplugged.org, where you can watch all sorts of fun astronomy videos, find out about upcoming episodes of this show, and many, many more. Now, our guest today will help us highlight some of the entries for the Astrophoto challenges and give us some insight both on the scientific and the artistic aspects of the entries. And our guests today are Angelo Ricarte and Elisa Pagan. Hello.
Hi.
Thank you guys for joining us. It's funny. You guys are so young and cheerful. People are going to think, oh, the old guy over there, he's the scientist, right? No. The pretty ones are the smart ones. Elisa, can you say hi to the folks and tell us a little bit about your work and what you do?
Yes. Hi, everyone. Thanks for joining us. I'm Elisa Pagan. I work at Space Telescope Science Institute within the Office of Public Outreach as a science visuals developer. And what that entails is really I get to create imagery, graphics, videos for news releases, educational resources, and other outreach products. And that's really with the intention of getting you guys and everyone involved in astronomy, disseminating scientific concepts, and just getting people excited. And the majority of what I do is I actually get to take Hubble data and soon other observatories like JWST, and also I work with other observatory data as well and get to make full color imagery that are hopefully compelling and engaging. And so, in other words, I get to make pretty pictures of space. So it's a pretty good gig.
That's a great gig. Angelo.
Yeah, happy to be here. My name is Angelo Ricarte. I'm a postdoctoral research fellow at the Harvard-Smithsonian Center for Astrophysics and the Black Hole Initiative. And as that name suggests, I'm interested in supermassive black holes at the centers of galaxies. I'm a theoretical astrophysicist, so I spend a lot of time running computer simulations and pondering equations, thinking about how black holes and their host galaxies co-evolve over billions of years. And I also work on the Event Horizon Telescope, which recently produced the very first real image of a supermassive black hole at the center of M87, it turns out. So M87 is probably my favorite galaxy in the universe, aside from our own.
Nice. Well, okay, so we have a theoretical astrophysicist, and I think I can call you an astrovisualist, couldn't I, Elisa?
That's fair, I think.
Okay, well, I think we've got everything covered. Now, just to let people know, this particular Astrophoto challenge asked the participants to capture their own real-time telescope image of M87 using the Micro Observatory Robotic Telescope Network, or you got to choose to work with an archived set of NASA and National Science Foundation data of M87. So basically, you got to, have control of the Micro Observatory telescope and get your own image, or you could take the archived image taken from multiple ground and space-based telescopes and take that data and create your image. Now, looks like many of the folks in our audience took up the challenge. How many folks? Oh, let me see who else we had out here. Do we have any other? Oh, Fatima. Thank you. Thank you for being here. And thank you for taking the challenge. And taking that data and turning into beautiful composite images. And they did that with a simplified version of a processing tool that professional astronomers use. Is that correct?
Yes. Mm-hmm.
Okay, so because I'm sure whatever you guys actually use would be way too big for our computers at home. It's like,
It
oh
can
gosh,
get pretty big.
nothing is running now. I can't, my email won't load. All right, well, let's get to it. Today we're highlighting some of the entries, hopefully some of the entries of the folks who are here because they want to see their work. And you guys will talk to us about those images that they created and tell us more about this galaxy M87. I mean, in particular, Angela, well, one, it's a galaxy that's named after a firecracker. No, that's not why it's named that. Is there a galaxy M80 where everything just keeps blowing up? No.
There must be. I don't know what it is. Well, it might be a nebula or something as well. Not all of the objects in the Messier catalog are galaxies.
I see.
This catalog was made by this French astronomer in the 1770s. He was looking for comets, and he wanted to. Okay, so I'm told that M80 is a globular cluster. So basically, he was looking for fuzzy things on the sky that weren't moving. Many of them are galaxies, but others are nebulae or globular clusters or sometimes other things. And M87 is interesting because it's a really massive galaxy. Actually, it's got an order of magnitude more stellar mass than our own Milky Way. And it's at the center of this cluster of galaxies called the Virgo cluster. So the center of one of the most massive gravitationally bound objects in the universe, which hosts one of the most massive supermassive black holes that we know of. And as these participants have noticed, that causes very spectacular stuff in many different wavelengths in this galaxy.
Oh, wow. So it's the center of a massive cluster with a massive black hole. So it's just big on big on big.
Mm-hmm.
That's incredible. That's our first compliment. Thank you. Oh, and we also had Vishal Kumar Patula, who's one of the Astrophoto Challenge winners. So thank you for being here too. Now, Elisa, can you tell the viewers, the folks watching who didn't take part in the Astrophoto Challenge, a little bit about the contest?
Yeah, so this contest is really about getting anyone at any astronomy literacy or interest the opportunity to do some of the work that astronomers and image processors do. So being able to do things like schedule time on a telescope and then being able to set parameters for those observations, like how long you want that telescope to take that image and capture that light, to things like sort of what wavelengths do you want to capture of light. So those are decisions that the contestants could make. And then also giving you the opportunity to work with data analysis software that astronomers use as well to examine the data in different spectrums and just learn a little bit more about it. And then, of course, taking your intuition and your creativity and applying it to the filters and the data and creating your unique, beautiful representation of M87. And so really it's just trying to give you a behind the scenes look of sort of what astronomers do and also allow you guys to see that like this data is for everybody. It's not just for scientists. And so hopefully this gives you some of the tools to either apply it on your own, whether you're just an astronomy enthusiast or whether this is something you want a career in.
Okay. Wow. Okay. So Yes, yes, Rachel, it is. M87 is cool, and so are Angelo and Lisa. So this is incredible. So they're getting data from the telescopes, and then turning that into imagery.
Mhm, mhm.
Now we're not just taking like numbers and plotting data on a graph. No, no,
Right. I mean, you
no.
can't
Well,
do
actually,
that if you wanted to.
just make waves. Yeah. Well, actually, let's look at some of these images. Oh, wow.
Yeah, this
Yeah,
is.
that's a lot better than any graph I ever made. Oh, wow.
Yeah, it's really enjoyable to see all of these at once because you just really see the different approaches that people took. Some people have more scientific leaning, just trying to like learn more about M87. Some people are focusing on one particular wavelength of light that they're stretching it so that we can see the brightness intensity. And that, like in this one right here, you can see it's color mapped, so the intensity actually kind of corresponds with the color. And so it's just really interesting to see the different ways that people approach this, and it's very fun.
Right. Yes, some look more photographic, some look almost whoa. What was that one? Okay, that's very non-photographic. That's really interesting. Some, like you said, are using colors to separate different wavelengths of light and distance and heat. This is incredible. Dormammu. That's funny.
Yeah, and people even chose different croppings, different focuses to emphasize on. So it really is just the sky's the limit with this kind of stuff.
Oh, wow.
Really.
Literally.
Yeah, I think it really goes to show that even with the same data set, different people can look at it in different ways and pick out new phenomena that other people haven't noticed before.
Okay, so those first ones were for the Micro Observatory challenge. These are from the NASA data?
Yes, yes. So the contestants have the opportunity to use either data, X-ray data from the Chandra Space Telescope. They could use optical data from the Hubble Space Telescope, radio data from the Very Large Array, and also infrared data from the Spitzer Space Telescope. So there's a lot to work with. So you can see lots of different combinations of the different parts of the spectrum. Some people chose to focus on one and some of the wavelengths just within that part of the spectrum, and then others choose to kind of use these multi-wavelength images. Were really interesting approach. We can see sort of how the jets are interacting with other parts of the galaxy in the dust and gas. And it just looks really cool. Some of these are just very like artistic and very interesting to look at.
Yes. Wow. So some of it is visual data, some of it is radio waves. That's but it's interesting how you can see that they're all, showing us the same galaxy. That there are visual through lines connecting all of these different interpretations.
Right.
Oh. Now, for anybody who joined us late, this is Ask the Astronomers Live, and we are looking at M87 galaxy images from the NASA Astrophoto challenges, and we're getting our minds blown
Right.
from all of these amazing different interpretations. Let me just look at the comments, see if we have any more of our contestants who've tuned in. Ah, Franco, yeah, that was your image. Vishal KP, gotcha. Oh, that's well. I'm great. Glad we have some people here. And so, if you guys have any questions about the Astrophoto Challenge or M87, or for Angelo's sake, the black hole at the center of M87, please be sure to put your questions in the comments. And those of you that's for the folks watching on Facebook or YouTube. Share your questions. Let's see.
Hey. Beautiful.
Yeah.
I think these really go to show why astronomers use telescopes at many different wavelengths. If you're only looking at the optical, you can see mostly the stars. Actually, you do see a little bit of this jet, but it's so much more obvious when you're looking at different wavelengths.
Mm-hmm.
Well, Angela, it was interesting what you were saying before when you were talking about the naming of galaxies and Messier. In the 1700s, Messier had the technology to see faraway galaxies, even back then?
Yeah, so there are even some galaxies that you can see with the naked eye if you're in the right place. The Southern Hemisphere has view of the satellite galaxies of the Milky Way, the Magellanic Clouds,
Really?
and you only need a pretty basic telescope in order to see some of these other objects, especially those in the Messier catalog. They're some of the most favorite what we call deep sky objects to target with relatively small telescopes.
Fascinating. So you don't need a gigantic telescope. You just need a good basic telescope and not to be standing in the middle of Times Square.
Yeah.
Oh, here's a really good question. Thank you, Vishal. I was wondering this myself. We're seeing in a lot of these images that line, that jet, that seems to be coming out of the M87. What are the jets that we're seeing in M87 made of? I guess this is probably one for you, Angelo.
Yeah, so what you're looking at is plasma that is moving near the speed of light that got launched from the vicinity of the black hole at the very center. This is material that almost made it in, that almost passed through the event horizon and got sucked in, but missed at the very last moment and instead got shot out into this jet that we see stretching for hundreds of thousands of light years here. And yeah, so it's very diffuse, but really fast and really hot plasma that we're seeing.
So the gravitational pull of the black hole was pulling it into the black hole, but then it didn't go in, and that gravity flung it and shot it away, and that's what made the jet. Oh.
Yeah, so a lot of the material does go in, but some of it gets spewed back out at the very last moment.
Wow, I'm sorry. I'm just having this image of a black hole as a 7-year-old trying to eat way too many cupcakes.
Exactly. Yeah.
Right.
Now, here's a question. Do all galaxies have black holes at their center?
We think that most of the massive ones do, massive being like Milky Way mass and larger. We're not sure about dwarf galaxies. Some of them don't even have really well-defined centers anyway. A lot of them look like irregular blobs. And because they're less massive, their gravitational pull is weaker, and that makes it a lot harder to find them. But many astronomers are trying to understand whether or not dwarf galaxies have black holes at their centers as well. But we think that most of the massive ones do.
Okay. And our galaxy has one?
Yep. 4 million times the mass of the sun.
Wow. So I'm guessing we don't have room for a lot of them.
Well, we think there are millions of little stellar mass black holes that are wandering around the galaxy, and there might also be wandering supermassive ones that would have came from old mergers with smaller mass galaxies. That was actually a subject of my most recent paper.
Wow. Oh, wait, another question. Oh, that's a good one about the images that we're looking at. Are we seeing This is an interesting question. Can you see a black hole? Are we seeing the black hole in any of these pictures?
Not in these pictures. So the Event Horizon Telescope was able to do it, but you actually need a spatial resolution about 5,000 times better than this. You need to use a very difficult technique called very long baseline interferometry, combining radio dishes around the world. Look up the Event Horizon Telescope if you want to learn more about that. But you are seeing its indirect effects, the jet that is coming from the center.
Now, I have a question for you, Elisa. Now, we're obviously looking at how people process these images, but what is processing an image at NASA? How is that compared to this sort of processing?
Yeah, so it's quite similar overall. The steps are very similar that you would take, in the sense that you have to retrieve the data. So you take your data files. You might have data in several different wavelengths or different filters. And usually for NASA releases, we have data for at least usually 3 filters, because we like to make a full color composite that's as natural and true to the science as possible. It won't always be the case. So depending kind of how the participants did this challenge, whether they wanted to use one filter versus several, it could be very similar. Yeah, for NASA, usually it's 3 filters, and then you take that data and then you have to scale it and stretch it in every of those filters in order to adjust those brightness values so you can start seeing the detail. Because at first it seems very black and dark, and so you really want to see that detail that's near the background level, so it's hidden. So you want to do that, and then that's when you start prescribing colors. And so normally for NASA releases, we use what we call chromatic order. So we assign colors based on ascending wavelength. So the shortest wavelength will be prescribed the blue, the highest energy, and then the longest wavelength will be prescribed the red, which is the less energy. And then in between we have the green, and that usually works very well. Of course, if we have more filters, we have to adjust it, and this is not always what we do. It's really a process, and you kind of have to go with the flow, and it depends on what the data that you have and the object that you're looking at. But after you combine that all together to make the full color image, that's where it really gets subjective, and it's really unique and individual in that way. And you start to apply more artistic principles, like things like contrast, color balancing, just color adjustments overall, orientation, composition, to really make like a compelling and informative, but also beautiful image. And so where kind of deviates as really sort of the state of the data files that you work with in the beginning. So the participants are working with very high level science products, so it's very, very clean. And image processors, we work with clean data as well. It's a very nice, but you'll still get some artifacts that remain just from the detector themselves. Things like cosmic rays that are hitting the detector. You get things called ghosts, which is just internal reflection. You can think of it sort of like a lens flare in your camera, just things that are not actually there. So you want to remove those not to distract the public. And also just sort of the motivation behind the way we process these images is a bit different, because you are usually working with a scientist that sort of it governs your approach of how you treat the data and the overall image as a whole. So those are the main things.
I mean, is it hard sometimes if you're looking at a new image to determine what's an artifact that's going to be removed, and what's something that is information that needs to be there?
There are times where it gets a little confusing. Like ghosts can be very close to maybe the center of like a galaxy, and you're wondering like, what am I looking at? Is that gas or dust? So it really depends on the orientation that you're looking at. But for the most part, there is a clear distinction, because either we know about those defects on the detector themselves, or stars have a gradient. There is what we call a point spread function. It's just, that's a star because it's not just this little dot in one pixel. Most of the time. So if it's a cosmic ray, you're like, oh, that's not supposed to be there, because that wouldn't be just one pixel, essentially.
Okay, so it's basically like cropping out the edge of your thumb from the photo you take.
Right. Yeah, you don't want that in there. That's confusing.
Right. Oh, wait, we have a great question from Rachel Zimmerman Brockman. Ooh, this is a good one. How far back in time are we looking when we're seeing these images of M87?
I know the answer to that one. It's yeah, it's 50 million light years away. So the light has been traveling 50 million years, which to me means, oh, we're basically not looking back in time at all on cosmic scales.
Right.
That's barely 50 million years.
Still early universe.
Right. Vishal Kumar Patola, is M87 red shifting or blue shifting? You'll have to answer that question and explain to me what red shifting and blue shifting are.
Elisa, do you want that one?
Sure, I guess there's a couple of ways to answer this. I'm going to go just for like the material near the black hole, because I think that might be the easiest way to talk about red shifting and blue shifting. Actually, one of the ways that we discover there's a black hole is because there's like an accretion disk it has a certain velocity. And just kind of like the Doppler shift, when something's coming towards you, it sounds higher, and then when it's moving away from you, it sounds lower. The same sort of phenomenon is happening. So as this gas and dust is moving away from you, it seems like it's red shifted. When it's coming towards you, it seems like it's blue shifted, and you can actually determine the velocity and therefore the mass at the center. So I don't know if that's what they were going for, but that is what I think could be helpful.
So the question is M87 moving away from us or toward us? Is that effectively
the entire galaxy?
Is that what red shifting, blue shifting means?
Right. Yes. Yeah. The light will be either red shifted or blue shifted, whether it's moving towards us red and then, away from us red and then towards us blue.
Yeah. So I can build on that. So for most of the galaxies in the universe, there is this cosmological redshift that's due to the fact that the universe itself is expanding and has been since the Big Bang. And since everything's moving away from us, things are typically redshifted. I'm actually not sure if that's the case for M87 though. The reason being that it's so nearby, and we're on the kind of on the outskirts of where you might of this Laniakea supercluster. We might actually be going towards it. I'm not sure.
Right. Yeah.
We'll need 50 million years to know.
The answer is probably available, but I don't know.
Okay, wait, we had a question here from Priyanko. If black holes eat everything, then why doesn't it eat the galaxy? Oh, good. This is some basic level black hole information that I need as well. Yes, if black holes have this massive gravity and they're pulling everything in, why is there still a galaxy around them?
Yeah, so I think it's a common misconception that a black hole acts like a kind of cosmic vacuum or vacuum cleaner, that it's pulling everything towards it. Actually, if the sun turned into a black hole right now, the Earth would keep going in its normal orbit. They pull on things just as much as something with an equivalent mass, as long as you're far enough away for relativistic effects to not matter. Weird things happen near the event horizon where gravity is really strong. You got to take into account the warping of space-time. The reason is that the black holes, as huge as they are not very massive compared to the galaxy overall. So the black hole at the center of M87 is 6.5 billion times the mass of the sun. The stellar mass of the galaxy is about 2 orders of magnitude more massive than that, and spread over a much larger area than the black hole's gravitational pull is really dominating. But if we gave it a very, very long time, much longer than the age of the universe, then things will eventually end up in black holes.
Right. Got it. Okay. Yeah. So Priyanko, the reason is black holes aren't so big that they can take in everything in the galaxy. They're, again, 7-year-olds eating the cupcakes. They can only eat what they can reach. Okay. Now, thank you guys so much. Now, but before we finish up, I wanted to ask you guys, Do you have any final thoughts you want to share with our audience? I mean, you've shared so much already today, so I understand if you don't. But Elisa,
Yeah.
anything before we say goodbye?
Yeah, well, first, I wanted to thank all the participants and anyone that's here today. Your involvement and your work in this is really important. I feel like it inspires others to get involved. And really, that's what this is all about, is spreading the astronomy love. We want people to get involved. That's what outreach is all about. So we're happy that you guys participate in this opportunity, and hopefully you guys will use these techniques later, whether it's just a hobby or you want to do something in astronomy career-wise. So yeah, the space is for everyone. The data is available to anyone, so anyone can play. So I encourage you to continue exploring. And I'll also have to say JWST, or James Webb Telescope, is coming around, so that gives us more data to play with. So I would say stick around for that.
Nice. Excellent. Angela?
I just want to say that this kind of data visualization is really important for the scientific process itself, not just for making pretty pictures, but for really getting the most out of your data and seeing things in a different way that other people might have missed. You could see from these many different versions of these images of M87 that one person can take this data and bring out different features than another person does. And it's important to keep playing with these kind of visualization schemes to learn more about your data set and see things in a new light and make new discoveries. And I spend a lot of time personally just replotting stuff that I already have to make sure I don't miss anything and make sure that it's as informative as my figures could possibly be. And so I hope everybody had fun and learned something from this.
Wow, that's so great. I mean, it's funny because when we think of science, a lot of times we think of it as dry and set. But Angela, that's an interesting aspect, that there is an aspect of individuality to, science. There's interpretation. Oh, wait, actually, thank you guys both for those great thoughts. But before we go, I have one more question I want to throw in, if we can. Oh, why does time, some gravity 201, why does time slow down near a black hole's event horizon? Anybody?
Sure. Well, anytime you're in a gravitational field, actually your clock, if you've got a clock, it'll be moving slower than if you were just in empty space. You can actually measure that effect, as small as it is, just comparing a clock here on Earth versus one that you send farther out at a larger distance from the center of the Earth. And when it comes to black holes or other compact objects, the effect really goes to the extreme, and it's hand in hand with redshifting as well, because in a way there's this the gravitational redshift, meaning that as you're in a strong gravitational field, the wavelengths of light get longer. That's kind of meaning that the separation in time as well of these troughs is changing.
Got it.
But yeah, basically very strong gravity that is even applicable in weaker gravitational fields too.
Wow. Gravity even time. All right. Well, now I guess our next show will be about time travel. So you guys will be back for that.
Or maybe we already were.
Exactly. No, Elisa, that's why you keep getting carded. It's your gravitational pull.
Oh, it's young forever. Right.
All right. Thank you both so much for being here and sharing your perspectives on the Astrophoto Challenge. And thank you to those of you guys who are watching, and especially, as Elisa said, thank you to everybody who took part in the Astrophoto Challenge. I guess right after this, I'm going to go on there and try to look at some more of those amazing images of M87. But for anybody else, you can see this video as well as all of our other videos on universeunplugged.org, or in Facebook and YouTube. Just click on the link we've got there in the comments. And in the future, for the future, make sure to subscribe to Universe Unplugged on YouTube, follow us on Facebook, so that you won't miss any of these fun type shows. All right, till next time, I'm Phil Lamar, and you have been Asking the Astronomers Live. Thanks for being here.